But I sent some videos on FFTs that like really explained it.
How long they go?
I'll send it again. I'll send it again.
Are you saying the square root? This square root now is square. Yeah, the square root of the left is equals to the other.
The square root of the left.
Realize what the structure is kind of
So you can go down, right, by squaring
yeah.
to the next.
Is it a square root or by root? What I'm talking about, I was talking about the one, the roots of unity structure now. I don't see a square root.
Oh, really? Can you see now? Okay. So to go up, you square,
Yeah.
and two things will give you the same square.
Yeah.
And to go up again, you square. Two things will give you the same square. And to go up again, you square. Two things will give you the same square also. So
Wait. This left,
yeah,
allow bottom now. The bottom let's see the weight at the weight. 1 minus 1, I minus I. That's the left.
this one, right?
Yeah.
Uh-huh.
So the square root of 1 is
You
1
have to come
minus
down this way, right?
Yeah, I was already talking. Yeah, the square root of 1 is 1 minus 1.
Yeah.
Alright?
Yeah.
The square root of minus 1 is I minus I.
Yeah.
So are you saying if we want to, if we evaluate 1 and minus 1, we just find square root of minus 1 to have I minus I?
Why are we finding square root of minus I?
No, you said the left has like still divided, like there's a way it's also divided. There is the other 4. There's a way that has no structure. So I'm wondering how I'm not
It's
seeing that.
like when you have root of unity, right?
Mm-hmm.
When you square it, you're going to get another set of roots of unity, but of half the size. So it's like this one now. This is the eighth root of unity. If you square everything there, you're going to get what? The fourth root of unity.
Yeah.
Then if you square everything there, you're going to get the second root of unity. And then this one will just be the fourth root of unity. Makes sense?
Are you going?
So you are now going to, you want to evaluate 8 values,
Mm-hmm.
the 8 root of unity. What you would do now is that your function that you want to evaluate, you are going to split it into g of x square, h of x square also, and then x that will be there, right? Now those two values are the g of x square and the h of x square. They don't need, it's like you're evaluating them on x square.
Mm-hmm.
So two values in those 8 will give you the same x square, right?
Yes, yes.
So that means that g of x square, you need to evaluate it at 4 points. Because it doesn't make sense to evaluate at 1 and minus 1 again, right?
Yeah.
Because it will give you the same value. Because g takes x square. Does that make sense?
Yeah.
And then h also takes x square. So from those 8 values, the g of x square and h of x square, you only need to evaluate it at 4 places.
Guys, if you want to do the 8,
Yes. That's if you want to do the 8. So you have like f of x. That's what you want to evaluate at 8 places. But this f of x can be written as what? Right? So those 8 values that you wanted to use here, That means that to get the value of f of x, you evaluate g of x at one of them, right?
Yeah.
H of x at the other one, at the same one, right? And then you also do this x thing here. But now, you have two things that the x squared is actually the same thing. So let's say you wanted to evaluate at f of 1 and f of minus 1. That's going to be g of what? 1, 1, right? Then this is g of what? 1 also.
Yeah.
So that your g of x and your h of x, you really only need to evaluate them at 4 places. Because of whatever answer you got when you were doing your f of 1 for your g of x squared, you can reuse it.
Okay.
You can reuse it there, right?
Yeah.
So let's say you wanted to evaluate as like 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, right? All you will need to do is evaluate at the square of all of them. That's 1. Makes sense?
Yeah.
Now, the problem is that with root of unity, this new thing I've gotten would also be a root of unity. But because I just use regular numbers, that's why it's not a root of unity. Make sense? So now this g of x squared is also a g of x on its own. That was just evaluated at x squared.
Okay, yeah.
So that means that it itself is representable with g1 of x squared correct? Any polynomial, any univariate polynomial is represented with this way,
Okay.
right?
Yeah.
So now you're evaluating this as 4 points, right? There are also root of unity points.
Okay.
So it means that you only need to evaluate this one at 2 points. So it's a recursive algorithm where you're just breaking it, going down, breaking it again,
So
going down. Yes. Then it's now take the result back up and start merging it with this x. They have done it, yeah. Uche and Ekarika have done it. Just watch the videos. I'll send it again. They are really good videos. Like they explain the theory and then they also show how it works. Yeah, effective. But if you want to implement FRI, you will need you need Merkle trees. You need an implementation of Merkle trees.
We have like Merkle.js for us.
Just write it yourself, bro. Write it yourself. It's a good experience.
And because of the proofs also.
Yeah.
We are not just hashing it together. We also have to get the proof
And verification.
and verification also to be able to say, okay, this is part of this. All those logic.
But in the lesson stuff, we are going to basically use a hash, right?
Yeah.
Yes.
Just choose the hash, right?
Yeah.
So it's not a big deal.
It's not a simple deal though.
Also.
It's not a simple deal,
But it's not a big deal. But it's not a simple deal. The reason why it's not simple is because of the index. Like if you hash A, comma B, it's different from B, comma A.
Yeah, we did that same thing when we factored that when we were handling our transcript as well.
So just
Transcript as well, the pattern, the order of appending also.
yeah. So you need Merkle trees. Then when you have Merkle trees, you need FFT. It's not compulsory, but if you want it to not be slow, you use FFT. If you don't care, then you just use your Lagrange interpolation. Then you evaluate your polynomial at all the roots of unity. Like you can generate roots of unity, the map polynomial the evaluate at x, and then you collect. That will be your code word. Or you use FFT. Then when you have that, you now do your FRI commitment phase, where you get the first code word, use your Merkle tree, you generate the Merkle roots, you put it in your commitment
In
struct.
your transcript.
Great. Okay. You're talking about non-interactive now.
Non-interactive.
Yes, you put in your.
It's not supposed to be interactive.
Hmm?
It's not supposed to be very interactive.
No, that's what you mean. But you still need to. You know, everything you're putting in your transcript is something that you were technically going to send
You
to.
were sent to
So that means you still need your
struct.
yes, that has all your commitments and your constants from the last. Then you will now need to generate queries that those A values that the verifier is going to say, okay, I want you to open A, then open minus A, then open A square. Then since you have opened A square, open minus A square, then open A4. Since you have opened A4, open minus A4, open A8, on and on like that. So the verifier is just generating like Meco authentication paths for every single one of them.
All these things you are saying, hope the recording is still on. Hope it's still
Yeah, this one
going
is- this one is still
into
on.
record. Please confirm that.
Please confirm, no worries. So yeah, after that, so all those things you're putting them into a structure. Your FRI proof. FRI proof is big, kind of.
Oh,
Then you now send that FRI proof to the verifier. The verifier would put all the commitments into the transcripts just to make sure that the query randomness is still the same. Then it's going to generate the query randomness also. Then it's now going to say, okay, for this first query, I'm expecting a set of Meco authentication paths, right? Let's say the first query is A. Then I'm expecting an authentication path for minus A, for A minus A, and A squared. So it's going to check the proof, and then get those three Meco authentication paths. It's going to verify each of those proofs to make sure that it matches the commitment that it was given. Then it's now going to use that F2 equals F1, blah blah blah, to ensure that those three values are consistent. Once it does that, it moves on to the next consistency check. Then it now goes to the next query.
so Meku authentication works in such a way that you have leaves, and the leaves pair together, leaves pair together, leaves pair together. If you want to prove a particular pairing, a particular hash, you now get the neighboring hash up to the root hash and stuff like that. But this one now works in such a way that when you have when I say give me the index for I, for instance, the other part I'm going to get is like minus I, then come down, get the square, get the, it's not straightforward like that. It's not really the same part as the Meku authentication part. So are we using, because I'm trying to get clarification, are we using Meku authentication system where you just get the relative hash rate, or are we trying to kind of like configure it in such a way that depending on the what the person the verifier is asking for, we just look for the negative and then start squaring, get the relative values for them and stuff like that.
So the verifier says that, okay, I'm querying A.
Yeah.
What it's asking for is like, what's the evaluation of F1 at A?
Yeah.
And what is also the evaluation of F1 at minus A? Then what is the evaluation of F2 at A squared? Right? It needs those three things to be able to do its consistency check. Right? But now, in order to make sure that you're actually giving me the correct evaluation at A minus A and A squared, what I'll require for you to do is you send me a Meco authentication path for A minus A and A squared.
Oh, not the whole proof.
The Meco authentication path is the proof.
Like not all the proof that has to do with that A. You know, the proof that has to do with that A might be like longer, like have more.
And for A now, they're going to send the neighbor.
Yeah.
This one just for A now.
Yeah.
They're going to send the neighbor.
Yeah,
Then you now know the hash of this, right?
Yes.
No. See, you are sending A, F of A, F of minus A, and F of A squared. That's what you're sending to the verifier. But along with each of those values, they're going to send one Meco authentication proof for each of them. Okay? Now the Meco authentication proof is all those hashes up to the root hash. You understand, right? So that call is going to happen in the next